There are different ways that a number can be random. We call these distributions. To understand the idea of a distribution, consider rolling a six-sided die, as in you have in any game. If you roll a die, you can only get answers like 1, 2, 3, 4, 5, and 6. You cannot get the answer 1/2, or pi, or 5/3, as those are not valid members of the underlying distribution. A distribution, therefore, is the set of possible values you can get and the likelihood that each has. We call the actual measurements samples. For instance, if we roll the die, we get 5, we say that 5 is our sample. Over time, if we sample enough, we expect to see, for this distribution, 1, 2, 3, 4, 5, and 6 occur equally frequently, and we expect to see no other values. Although dozens of distributions are commonly used, in CS 101 we are primarily interested in 3, the discrete integer distribution, the uniform distribution, and the normal distribution. These 3 distributions describe many of the scenarios that we need to model commonly in engineering and science, and you should learn to identify each one of them on site given enough samples. Discrete distributions are the random numbers of choice. Typically, we're sampling one value from a set of counting numbers, starting with 1 and running up. For instance, this could be flipping a coin, or rolling a die, or drawing a card. For instance, if we consider rolling a die, as demonstrated here, we can get the values 1, 2, 3, 4, 5, and 6. These are the values across the x-axis in this diagram, with probabilities up the y-axis. And in this case, each one of them has a probability of 1/6. If we would like to model this in NumPy, we can use numpy.random. We've already set the seed the way that we saw previously. We can say np.random.randint. We'll give it the values 1 through 7. 1 is inclusive, 7 is exclusive. Most of the time, our random number functions inside of np.random behave like range, where they're inclusive on the left-hand bound and they're exclusive on the right-hand bound. If I run this value, I get 4, 2, 6, 4, and as I continue to run it, I get the next values in this sequence. Another way I can simulate this same set of values, 1, 2, 3, 4, 5, 6, is to provide 6 only, which implies a left-hand bound of 0, but excludes the right-hand bound of 6, giving us a range 0, 1, 2, 3, 4, 5, and then add 1 to it, which gives me the same range, 1, 2, 3, 4, 5, 6. I can also simulate rolling multiple dice at once. np.random.randint, I'll give it 1 through 7, and I'll say size equals 5. This is rolling 5 dice the way you would in a game like Yahtzee. I see 1, 6, 5, 5, 1. I see 6, 5, 6, 1, 2. I see 4, 3, 1, 4, 6. A visual depiction of the values would show them lying in discrete bands with no intermediate values such as 3.5. In this example here, I will generate 1,000 values. You notice I've set this up as a tuple, but I will simplify that to a single number. We're going to choose 1,000 values, equivalent to rolling 1,000 six-sided dice. And we're going to plot these as red dots using pyplot. You can see across the x-axis the value of each time we rolled the dice, and up the y-axis the different values that occur, 1, 2, 3, 4, 5, and 6, with no other values lying in between them. In general, if we examine a distribution and we see this kind of banded behavior, we can suspect that a discrete integer distribution was used to generate the data originally. The most commonly used random distribution on a computer is what is known as the uniform distribution. This yields any value between 0 and 1 with equal probability for all of those values, and it doesn't yield anything outside of that range. In principle, it could also include the limit 0 or 1, but because it's giving you a float value back, something like 0.7135, etc., that's extremely unlikely. Uniform distributions describe the randomness of probability. For instance, if we're saying that there's a 50% chance of something occurring, or a 5% chance, or a 6.7% chance. np.random.uniform produces these values. Each time I run this, I will get a new float between 0 and 1. And across that range, they will be equally likely with each other. Other ranges are also possible. For instance, in this scenario, I've given it the range -1 through 4, and it will choose anything in that range. If I pass uniform the size parameter, as I did previously with randint, I can also affect the source of things that it sees. So here I'll go from -1 to 1, and I will select 20 values from that range, and it will generate these for me again as a one-dimensional vector in NumPy. If I examine the distribution of these the same way that I did with random integers, I expected with random integers to see bands. With uniform values, I expect to see basically noise, static, in between whatever range that I select. For instance, in this case, I'm going to have regular uniform random numbers. I'm going to select 1,000 of them, and I'm going to plot them as blue circles. And in this case, you can see that for the 1,000 values across the x-axis, 0 to 1,000, I only have values lying in between 0.0 and 1.0 as expected. The random integer and the uniform distribution both select their values with essentially equal probability across their range, given their respective constraints. In contrast, the normal distribution selects how close things are to their expected average. This is a different kind of randomness. It's often described as a bell curve. It's the randomness that you see in measurements in an experiment. It's a randomness that you see in demographics, in grading, in a lot of other kinds of statistics. A normal random number can be positive or negative, but each random number tends to be centered around the mean of x equals 0, the origin, and it has a standard deviation or a likelihood of being far away from that of 1.0. Here you can see the values across the x-axis, that it's very unlikely for us to see, say, a value like -4, 4 standard deviations out. It's relatively more likely for us to see a value of -2 or +2. But it's most likely of all for us to see a value at 0 or very, very close to it. And indeed, most of the values generated by random normal numbers will lie close to 0. np.random.normal by itself generates these numbers. Although many of these numbers will lie in the same range as uniform random numbers of 0 to 1, you will also see negative numbers, and you will occasionally see numbers that lie farther out than that. If we run this enough times, we will find numbers like -1.467 that lies farther outside the range than what we would ever see with a uniform distribution. Now, we could define a uniform distribution that went from, say, -2 to +2. How would we distinguish? We'd have to plot and look at the way that these things are distributed separately from each other. In this case, I'm going to generate 1,000 random normal numbers, and I'm going to plot them as blue circles using pyplot. You'll notice here that they're all clustered around the 0, the x-axis, and they become sparser as you move farther and farther away from that point. So rather than being equally distributed within two bounds, they tend to cluster around a central point, and they get more diffuse as you move farther away from that. np.random.normal with size, as we just saw, generates other values for us. But what if we need to do things like change the mean or change the kind of distribution that happens? np.random.normal plus 10 changes the mean from 0 to 10. And you'll notice now that most of our numbers are going to be very close to 10, and they're going to be centered around 10. That's the new mean of our distribution. If we want to model this with a standard deviation of 2, we would need to write something like np.random.normal. There's an argument called scale that you would pass in. So we'll give it a standard deviation of 2. This will give us things that are more dispersed from the others. And then I can do things like then move my mean. I need to do these things in the right order, and they'll show up naturally for me. For instance here, this is a random number selected from the normal distribution with mean 1 and standard deviation 1. We've added 1 to it to shift the entire thing to the right. Here's one with mean 0 and standard deviation 4. This sort of smears out our bell curve so that we see the values distributed over a much broader range. We can also combine both of those features as I showed a moment ago in code. np.random.normal with a scale of 4 and a mean of 1. One common application of random numbers is in making games. This makes it easy for us to make things adaptive or responsive in ways that otherwise we would find very dull and predictable. For instance, if we want to make a simple guessing game, we can say number equals numpy.random.randint. We'll take a value from 0 through 9, and then we'll add 1 to it, which puts it in the more human natural range of 1 through 10, only including random integers. We'll set up a guess using input. Guess the number between 1 and 10, at which point anything can be typed by the human interacting with this program. We actually don't know what number is at this point. While int guess, remember that input always gives us back a string, is not equal to number, guess equals input. Nope. Try again. When that's complete, that while loop will exit, and we will print a congratulatory message. Try 1, 2, 3, 4, 5, 6, 7. So 7 is our answer there. We've successfully detected this. Another common task is to randomly sample a value, something like drawing a card from a deck of cards. For instance, here, if we have a list of colors named X, which contains strings red, yellow, blue, jail, and olfire, if we run np.random.choice, it will randomly pull out one of these. Here I'll call it colors, red, yellow, blue, jail, olfire, np.random.choice, colors, and will return to us one of those values. It threw me a little bit because most of the time it's still picking blue. That's random and unpredictable. However, it's not centering on anything. That's just the particular random sequence that I got just then. Choice also lets us simulate things like drawing a number of values, for instance, from a deck of cards. So here you can see a code block that sets up a deck as a NumPy array from 1 through 52 inclusive. np.random.choice is then given the deck to draw from. It's told to draw 5 cards, and it has this new keyword replace that's being passed in there. Replace is set to false. Now, if you're drawing a deck of cards, you're up on stage with a magician, you're drawing from a deck of cards, and you look down and you've drawn 3 jacks of hearts, immediately you're going to think that something's up with the deck. Something's not behaving properly. Replace means that once a value has been drawn from the deck, it's no longer considered for probability in the subsequent set of choices that is made. This is desirable when we're doing things like drawing from a deck. If we're doing something like grabbing a random number from die rolls, then we don't want to replace it because die rolls can occur repeatedly. There's also shuffle. Shuffle randomly reorders something in place. So if I set up deck equals np.array, range 1 through 53, and so if we look at deck now, we see all of our cards in order. Every number is assigned to a unique card. np.random.shuffle. Doesn't return anything, but it alters the deck in place. So choice returns to you one of the things that's inside of your selected container. You can use choice with a list, you can use choice with a vector or some other kind of array. Shuffle doesn't return anything at all. It just alters that in place. So that's something to be careful with when you work with choice and shuffle. Take a moment, read this question, and determine which of the following will not reproduce the behavior of a six-sided die in C. In other words, 3 of these 4 answers will successfully reproduce the behavior of a six-sided die. 1 of them will not. Pause the video now and decide which one of these does not behave like a six-sided die based on what we've learned so far. Our answer is C. If we examine these from the bottom up, we can see that D sets up a value D, np.random.uniform times 6, so it's selecting a value between 0 and 6. It's taking the integer representation of that, so it's going to chop off the decimal fractional part and just leave the whole number part. 0, 1, 2, 3, 4, 5 would be what was left in that range. And it's going to add 1 to it. 1, 2, 3, 4, 5, 6. So D successfully reproduces the behavior of a six-sided die. C is similar to what we've seen before, where we're selecting random values 0, 1, 2, 3, 4, 5, adding 1. B is also similar. We're setting up an array with a range 1 through 7, exclusive, so 1 through 6. And we're using random.choice to pull out one of those values. A, in contrast, is using a normal distribution, which we typically use to describe measurements or observations of, say, instrumentation. Normal values are centered on a particular number, like 0. And so you get positive and negative values. It won't look anything like what's happening with a six-sided die.